day everyone. Today is another class of physics. This presentation or this class is for grade 12. In this class we will cover or we will finish chapter 4 and then we will move to chapter 5. This presentation is for week 5 and presented by me, Mr. Khalid. Actually, this presentation consists of four main parts. The first part is the torque of a couple, and then we will move to pure turning effect. Number 3 is a summary of chapter 4, and then we will move to chapter 5, which will cover work, energy, and power, and what's the relation between three of them. Work, energy, and power. We will start with the torque of a couple. It's a special case of moments, what we have done in last presentation or in the last class. As we can see here in figure 425, so the forces here, there are two forces. One force in this direction, which is 15 Newton, and another one is 15 Newton in opposite direction, and the distance between this force at the center here is 0.2 meter. It's up to here, and the distance between this force and the center here is also 0.2 meter. So this figure shows the forces needed to turn the car's steering wheel, and this forces is needed to turning what the car's steering wheel. So the two forces balance up and down. One is balance up and the another is balance down, and both of them is 15 Newton. They are what? Same forces. So the wheel will not move up or down or sideways, because the forces are same, 15, so the wheel will not move up or down or sideways. However, the wheel is not what? In equilibrium. The wheel of the car is not in equilibrium, so the power of the two forces here will cause what? It to rotate. The power of force here, it's a special case. It's not like this, like the same condition in last presentation. So the power of forces here will cause it to rotate. Now we need to calculate what the forces or the total forces here. So a power of forces here in this figure, in figure 25, is known as what? A couple. So a power of forces like that in figure 425 is known as what? A couple. So what's a couple? A couple here has a turning effect, but doesn't what? Cause an object to accelerate. This is the couple. A couple has what? Turning effect, but doesn't cause an object to accelerate. So from or to form or to have a special case like this, there are two forces must be in here. The two forces must be what? In 2 or 3 conditions. Those forces here, this force and another force here, must meet what? 3 conditions. So to form a couple, the two forces must be, first one, equal in what? In magnitude. They are equal what? In magnitude, or the value are same, 15. This first condition. The second one, what? The two forces must be what? In parallel. They are in parallel. This one force here and the other one is here, so they are what? In parallel, but what? Opposite direction. Parallel and at the same time in opposite direction. This one is in this direction and the other one is in this direction. So they are in opposite, parallel, opposite direction. The third one, they must be separated by a distance. They must be separated by distance. This is D, the distance D. D is equal to 0.2 plus, in this example, 0.2 plus 0.2. So to form a couple, or to be in this condition, a special case here in a couple, the two forces must be equal in magnitude, parallel but opposite in direction, separated by distance D. Okay, now in this special case, as we said, this is a special case from how to find the moment. In this special case, we need to find what the turning effect or moment. The turning effect or a moment of this object. So the turning effect or a moment of a couple is known as what? A torque. Is known as a torque. Because this one, as we said, is a special case from the previous one. So now we are focusing to find what? The torque of a couple. Torque of a couple, it's exactly same what as we said in last presentation. This is what? This is a moment. It is a moment. So we can say the torque of a couple. In last one we said a moment. So the turning effect or moment of a couple is known as we said, is known as what? Its torque. So now we are going to calculate the torque of a couple in figure 25. In figure 25 by adding moments of each force about the center of what? Of wheel. So what's the torque of a couple? The torque of a couple, as we said before, it's a force. It's a force. It's equal to F times D. F times, let us see, D. F is a force, D is what? Distance. Distance from where? From the center here. So the torque of a couple is equal to 15 times what? 0.2 meter. 15 Newton times 2 meter. This is for this force or for this part. This one, because this one in an opposite direction, plus 15 times what? 0.2. So it's equal to what? 6 Newton meter. 6 Newton meter. Actually, there's another way to find the torque of a couple. By what? So we could have found the same result for this figure by multiplying one of the forces, one force, because they are same, 15, 15, by what? Perpendicular distance between them. By perpendicular distance between them. The distance between them is what? Between this force and this force is equal to what? This distance, D1 plus D2. So the torque of a couple is equal to what? 15, one of the forces, same, 15, 15, times what? The whole distance between the two forces, which equal to 0.2 plus 0.2 equal to 0.4. 15 times 0.4, we will get the same result, 6 Newton meter. So the torque of a couple is defined as follows. The torque of a couple, we can define it as follows. A torque of a couple is equal to what? One of the forces times perpendicular distance between the forces. As we have done in this example here. So one of the forces times what? Perpendicular distance between the two forces. Okay, now we will move to another title, which is pure turning effect. What's the meaning of pure turning effect? So now when a pure turning effect here, when we calculate the moment of a single force is different from the moment of what? a couple. We have done this one in last class, and today we have a turning effect or a moment of a couple. So when we calculate the moment of a signal force, the result depends on what? The point of what? Pivot. The point of pivot, about which the moments act. So we have like one moment in clockwise sometimes, and the other one in what? Anti-clockwise. So we said last presentation that the clockwise moments here is equal to what? Equal to anti-clockwise. Anti-clockwise, we have two forces, or it depends on what? The result here, or the total moment, it depends on what? Depends on the point of what? Pivot. So the further the force, as we said, if the pivot is here and one of the forces is here, if one, for example, if one is here with distance d1 is different from what? F2 with distance d2. How? The further the force from the pivot, the further the force, like F1 here, it's far from the pivot here compared to F2. So the further the force is from the pivot, the greater what? The moment. So the moment here is what? Greater than the moment here. In a couple is different. If we have a couple of forces, is different. The moment of a couple doesn't depend on what? The point about which it acts. Only on what? Perpendicular. So the moment here, it depends on what? It not depends on the pivot here, but it depends on only on what? Perpendicular distance between the two forces. A single force acting on object will tend to make an object accelerate. So a couple here, however, is a pair of what? Of equal and opposite forces, as we said. So it will not make the object accelerate. This means we can think of a couple as what? Pure turning effect. So for any object to be in equilibrium, two conditions must be met at the same time. First one, the resultant force acting on this object is what? Zero. It's zero. And the second one, the resultant moment must be zero. So for any object to be in equilibrium, there are two conditions here, must be met at the same time. Must be met at the same time. Resultant force is equal to zero. Resultant moment is equal to zero as well. So it's different between the moment, or the pure turning effect is different from single force and a couple of forces. Okay. Now we will move to have some example or work with example here. We will solve the work with example number 8. Actually in your book is number 10, but in our example is here in our classes is number 8. As we can see here in this example, the driving wheel of a car traveling at a constant velocity has a torque of 137 Newton meter. So what's this? This the torque of what? Of a couple is equal to what? 137 Newton meter applied to it. So that drives the car here. So the radius from the figure here, the radius from here up to the ground here is equal to what? 0.18 meter. 18 meter. So what will we need here? We need to calculate the driving force provided by this wheel. We need to find what the force. We have what? We have the torque of a cable, 137 Newton meter, and we have the force. We need to find the force actually times what? Distance. The distance is what? 0.18 meter. So F is equal to what? F is equal to 137 Newton meter over what? 0.18 what? 0.18 meter. So meter with meter, so it's still 137 over 0.18, which is equal to 761 what? Newton. So the force needed here is what? Is equal to 761 Newton to make this wheel moving. So what we have? We have to draw or to write the formula here. The torque of a cable is equal to perpendicular distance times force times what? Perpendicular distance. We have this one is given here in this question. Velocity has a torque of 137 Newton meter, and we need to find F, and the distance is what? 0.18 meter. So F is equal to torque of a cable over what? D. It's equal to 761 meter. Okay. Now we will take like a summary on chapter number 4. This is the key points to cover the whole chapter. First, we need to mention that forces are vector quantities that can be added by means of what? Vector triangle, as we do in last classes. So forces are what? Vector quantities that can be added by what? Means of vector triangle. This first one. Second one, those points is very important. They cover the whole chapter. You need to keep them very clear. Vectors such as forces can be resolved into what? Into components. Components are at right angle to one another, can be treated independently of one another. How? For any force F at angle what? Theta to the x direction, so the components are what? X direction is what? In x direction the force is what? F cosine theta. The force acting or at the x direction is equal to F cosine theta, and then another force is at y direction is F sine theta. So this force is the force F has two components, one in y direction and another one in x direction. In x direction F is equal to F cosine theta, in y direction F is equal F sine theta. Okay, the third one here, the moment of a force is equal to what? Force times perpendicular distance from where? Pivot. So the moment of any force is equal to the force times perpendicular distance of what? The pivot. From where? From the line of acting of the force. From line of action of the force. Number 4, the principle of moments states that for any object that is in equilibrium, must be in equilibrium, the summation of what? This, it's very important. We solve lots of examples by this formula, or by this thing here. What we say here, we said for any object that is in equilibrium, what happened? The summation of clockwise moments about any point provided by the force acting on the object equals to what? The summation of anti-clockwise moments about where the same point, which usually be the B foot. It's usually this point B, or located at the B foot. So the total of this one, the principle of moments, state that for any object that is in equilibrium, the summation of clockwise is equal to what? The summation of anti-clockwise moments. Number 5 is a couple is a pair of what? Of equal, as we said last slides, a couple is a pair of equal what? Equal, parallel, and what? Opposite. 3 conditions: equal, parallel, opposite forces, whose effect is to produce what? A turning effect on a body without giving it linear acceleration. It's a special case from where this one is special case from this one. So the torque of a couple equal to what? One of the forces times perpendicular distance between the forces. Finally, for any object, or for an object to be in equilibrium, the resultant force acting on the object must be 0. First one must be 0, and the resultant moment must be also 0. Both of them are 0 because this object what? In equilibrium. So those points here, 6 or 7 points here, they cover the whole chapter, chapter 4. Now we will move to chapter number 5. Chapter number 5 is focusing on what? Or will start with work, energy, and power. This is very important chapter. They are very interesting topics here. Work, energy, and power. So what's the meaning of work, energy, power, and what's the relation between them? We will start with doing work, transfer energy. Doing work, transferring energy. Means what? If you are going to do work, so you are going to what? Transfer energy from one object to another object. As we can see here in this figure, I think this figure is figure 5.3. So the weightlifter here shown in this figure has a powerful muscles. It's a powerful muscles. They can provide the force. There is a force transferred from where? From his body to where? To those things here, to the weight here. So provided the force needed to lift what? A large weight above her head. So this one, or the weightlifter here, can take this one from the ground and move it approximately, it's about 2 meters up above her head here. So the force here exerted here, the force exerted by the weightlifter transfers what? Energy from here. There is an energy from here to what? To the weights. It's a transferring energy from here to where? To the weights. Okay. So as she lifts the weight, or the weights, and transfer energy to them, we see that her lifting force is doing what? Work, because she is lifting the force, and she will do what? Doing work. It's a work. So what's a doing work? Doing work is a way of transferring what? Energy from what? One object to another. as we say in last figure, there is an energy transferring from her body to where? To the weights. So doing work is what is a way of transferring energy. There is an energy need to be transferred to what? To the weights, or from one object to another. So work and energy are two closely linked concepts. They are very close to each other. In this table here, table 5.1, describes some situations which illustrate the meaning of doing work in physics. So we have some examples here. Doing work, not doing work. Here, pushing a car to start it moving. It's doing work. Pushing a car, but the car doesn't move, so not doing work. Lifting weights, you are doing what? Work. Holding weights above your head, so you are not doing any work. So those some examples from everyday life, examples of doing work, not doing work. Falling stone here, the moon uprighting the earth. So this one not doing a work. Here we are doing what? A work. So there are different examples of doing and not doing work. Okay, now we are moving to another topic or subtopic, calculating work done. So what's the value or how we could calculate the work done? Any force can transfer what? As we said before, transfer energy from where? From you to the car. A force transfers energy, here this figure, energy from you to what? To the car. But how much work do you do? How much the work, or how could we measure the work you do? In this figure here shows two forces or two factors involved here in this figure. First one, the size of the force F or the value of the force F. So how the force here can change the forces or the factors here in this figure. The bigger the force, what? The greater the moment of what work you do, or the greater the force, if the force is high and higher and higher, so the amount of work you do is what? Is greater. It depends. It's what do you say? It's a strong relation between the force you do, and what amount of work you do. So the bigger the force you do, the greater the amount of work you do. The distance is or x here. Let us say this is the distance is. You push the car. So the further you push it, the greater the amount of work you done. If you push this car for example 5 meter, is different from to push the car for 10 meter. For 5 meter you need to do for example small work to push the car, and if you are going to push it for 10 meter you need to do what? More work need to be done to push what? The car, because the distance is what? Is greater. So there are two things here, or two factors involved, which they are the force F. The bigger the force, the greater the amount of the work, and what the distance is. You push the car, so the further you push it, the greater is the amount of work done. So the bigger the force, the further what, and the further it moves, the greater amount of work done. Say the relation now. The bigger the force, if the force is higher and the further it moves, you need to push it more further, the greater of amount or the amount of work done. You need lots of work done to push the car to this distance. Okay. Now we will go to work done. Here we need to do some formula to calculate the work done. So the work done by any force is defined as the product of the force and the distance moved in direction of the force. So the work is equal to what? F times S. F times S, where S is the distance moved in the direction of the force. In this example or previous one, for that example shown in figure 5.4, F is equal to 300 Newton and S is equal to 5 meter. So what's the work here? The work is equal to W. This is the formula. W is equal to what? F times S, force times distance, is equal to what? 300 times 0.5 is equal to what? 1500 joule. So the work is calculating by what? Joule. And the work done is equal what? F times S. And the work done here, the value of the work, it depends on what? F and S. If F is higher, so the work is more. If the distance is greater than the previous one, or the distance is higher, so the work is what? Is higher. It depends on two values here, F and S. F and S. So this is how we could work or measure the work done by force. It's measured by what? The work here is F times S and measured by what? Joules. I think this is all for today. For next class we will move to energy transferred, another topic on the same chapter. We will cover the whole chapter inshallah and finish the whole chapter in next presentation. That's all for today. Thanks for listening. Any questions, I am happy to answer your question. Thanks.